Learn like a pro.
Welcome to The Explainer. Today, we're going to dig into the invisible forces that are constantly at play, governing every single moving object around us. You know, from something as simple as a block on a table to a skydiver hurtling towards the earth.
I mean, have you ever really thought about it? You push a book, it slides for a bit, and then it stops. You roll a ball, and no matter how hard you throw it, it eventually comes to a rest. It feels like this universal law, but why? What is this invisible brake that's always being applied to everything?
Well, that answer is a force we call friction. It is everywhere. And honestly, understanding how it works is the key to unlocking the physics of motion itself. It doesn't matter if we're talking about an object sliding across a floor or literally falling through the sky.
Okay, so here's our game plan. We're going to start by defining what this unseen force even is. Then we'll see how it creates balance, or, a lack of balance. We'll explore its kind of dual nature, how it can be both a friend and a foe, and then we'll wrap it all up by applying everything to the really dramatic physics of free fall.
So, first things first. What exactly is this force that seems to want to stop everything from moving?
The two big words to pull out of this definition are contact and opposes. It's a contact force, which just means the surfaces have to actually be touching, and it always opposes motion. No matter which way you try to move something, friction is right there pushing back against you. It's a cosmic contrarian.
Now, this is where it gets really cool, because this slide pulls back the curtain on what friction actually is. It's not magic. If you could zoom in, way in on any surface that looks perfectly smooth, you'd find all these microscopic hills and valleys. Friction is literally just those little bumps and grooves on one surface catching and interlocking with the ones on the other surface. That's the resistance you feel.
All right, so now that we know what friction is at a tiny level, let's see how this idea builds into the fundamental laws of motion. It all really comes down to a constant battle between the force you apply and the friction that pushes back. So, in this first situation, we're pushing a block with exactly 20 newtons of force. That's just the unit we use, don't worry about it. And look at that. The frictional force pushing back is also exactly 20 newtons. It's a perfect stalemate. The forces are balanced. That means the net force is zero, so the block doesn't speed up, it doesn't slow down, it just keeps on cruising at a steady speed. But what happens when we really put some muscle into it? Now we've cranked our push up to 68 newtons, but that friction is still stuck back at 20. All of a sudden the forces are unbalanced. We've got a leftover or net force of 48 newtons pushing the block forward. And according to Newton's second law, an unbalanced force causes acceleration. The block starts picking up speed. Simple as that.
Okay, we've got the mechanics down. Let's zoom out from the physics problems, because this force plays this constant kind of dual role in our everyday lives.
And this chart just illustrates that split personality perfectly. On one hand, friction is our absolute best friend. It's the only reason you can walk without your feet slipping out from under you. It's why your car's tires can grip the road. But on the other hand, it can be a real nuisance. It's what causes machine parts to wear down and break, and it wastes a ton of useful energy as heat.
And because of that annoying side, engineers have gotten incredibly clever at taming friction. They use tricks like ball bearings and wheels to switch from sliding to rolling, which is way easier. Or they'll add lubricants like oil to make those microscopic surfaces way smoother. The whole goal is just to make our machines more efficient.
All right, it's time to put it all together. Let's take everything we've talked about and apply it to the ultimate example, an object in free fall. This is where friction in the form of air resistance really takes center stage, and believe me, this is where things get interesting.
So first, we have to separate the physics textbook world from our world. In a perfect vacuum, where there's zero air, gravity is the only force that matters. A feather and a bowling ball will fall at the exact same rate. But out here, in our atmosphere, we have air resistance, which is really just a type of fluid friction, and it's constantly pushing up on falling objects. And that changes absolutely everything.
Now, the really important thing to get here is that air resistance isn't some fixed number. It's a dynamic force, and it's always changing based on three key things. 1, the faster you go, the more resistance you feel. 2, the denser the air is, the more resistance. And 3, this is the big one, the larger your surface area, the more air you have to push out of the way, and the greater the resistance.
This graph just nails the first phase of a skydive. Let's walk through it. At point A, you've just jumped out of the plane. Your speed is low, so air resistance is tiny, and you accelerate like a rock. But as your speed picks up, so does that upward push from air resistance, which you can see at point B. This starts to cancel out some of gravity's pull, so your acceleration actually starts to slow down. Finally, at point C, you hit the sweet spot. You're moving so fast that the upward force of air resistance perfectly balances the downward force of your own weight. The forces are in equilibrium again. Your acceleration drops to 0, and you are now falling at a constant maximum speed. We call that terminal velocity.
And then, you pull the ripcord and phase 2 begins. At point D, the parachute just explodes open, massively increasing your surface area. This causes an enormous, instant spike in air resistance. The upward force is now way, way bigger than your weight, which creates a huge net force upwards that basically slams on the brakes. You decelerate, and you do it fast. Then, as you slow down, the air resistance drops off until once again it perfectly balances your weight at point E. You've just reached a brand new, much slower, and thankfully much safer terminal velocity to land with.
So, from the microscopic interlocking of surfaces all the way to the life-saving mechanics of a parachute, friction is this universal force that both opposes motion and, in a weird way, makes it possible. It's the world's constant, unseen pushback. You know, it really makes you wonder, if friction is the force that stops motion, what unseen forces are you pushing against every day just to keep moving forward?